Welcome to this series of lectures on dynamical systems. Nonlinear dynamics refers to those categories of equations which are characterized by nonlinearities in some way or the other. And while we've looked at linear equations, there's a host of methods with which we can solve linear equations. Typically, nonlinear equations are not solvable, and it is very difficult to discern what kind of behavior such nonlinear systems would have. And while they're difficult to solve, they're quite prevalent in nature. Almost every fluid mechanics problem or predicting weather, they involve some kind of equations which have a very contrived feedback. So the evolution of the system keeps changing the system in such a way that it becomes very difficult to keep a track of all the variables. Moreover, various engineering systems which involve lasers, microwaves, phase locked arrays, things which are very common in communications, they also rely heavily on how you can analyze these systems from a nonlinear dynamics perspective. The original idea behind all of this was whether or not we can predict trajectories of planets. If you have a two body system, we know from Kepler's law that you can find out the momentum, the velocity, the position, all these things. But the moment you have a three body system, it becomes almost impossible to find out the exact dynamics at a given point in time in the future. However, there are some other questions that we can pose which can help us in understanding the system rather than knowing at what point will a planet be at a given time. We can ask the question whether this three planet system is stable, whether one of the planets will be flung off to infinity, or whether the three planets will collide. These are the kind of questions that give us insight into such kinds of systems. In this series of lectures, we'll first see how to analyze various problems geometrically. So, nonlinear dynamics relies heavily on visualizing the solution rather than solving the equation. You'll see that often you're not solving the equation, but you're trying to find out a way in which you can sort of classify how the system would behave. Based on that, you can make various kinds of predictions. So, after studying how to interpret equations geometrically, we will look briefly into what bifurcations are. Bifurcations refer to the situation where a parameter, when it changes, it can seemingly cause the system to behave quite differently than it was. Consider, for example, the buckling of a beam. When you take a beam like this and you put normal stress, normal compressive stress, nothing happens. But at a certain point, if you take a twig and try to compress it, you'll see that it bends. Okay, so that kind of a change in uh, qualitative behavior occurs because of some parameters which are related to not only the loading but the material properties, the material shape, and all these things. They end up dictating how the system will behave and whether or not that behavior will change its qualitative behavior dramatically. So let's begin our journey by analyzing things geometrically. So let me create a new file. Alright, so let us consider a very simple nonlinear differential equation. So let us consider ddt of x is equal to sine x. So it's a very straightforward equation, and of course it's a nonlinear equation because sine makes it nonlinear, and it's an autonomous equation. That is, the right hand side, it does not depend on time. Now we can integrate this particular equation. In fact, the solution to this is the solution is given by log of this entire thing, and obviously it has to be positive. So now what do we do with the solution? Obviously you cannot, it's not easy to tell what the solution means. I mean, you have a bunch of cosec, cot. I mean, just looking at it, you cannot really tell what happens at long times. First of all, it's a implicit way of representing the solution. That is, you would expect x to be a function of time, but here you have been given the inverse. You have been said that given this x, this is what the time you expect it to be. So first things first, let us look at how this function looks like, keeping in mind that it is not a explicit function where x is given as a function of time. So we obviously must make an implicit plot. Okay, so let us create the domain on which we want to make the implicit plot. So let us import, in fact let me copy this bit of code. We will require it in this study as well. So we are importing numpy, matplotlib, we are updating the matplotlib parameters, we are making the inline figure to svg, and we are importing ipy widgets. Okay, so let me execute this. Let x, let t be a linspace from 1e minus 6 to 10, and let me take 100 points. Let x be a linspace from 1e minus 6 to 4 times pi. Let me take 100 points in this. And the reason why I'm choosing 1e minus 6 is because I don't want this to be 0, because log of, so 0 is fine for time, but once we have 0 appearing in the inside the log, it will blow up. So I want to avoid dealing with those, and you can later on play with this and see what happens. Okay, so I've defined the two things. Let me create a mesh grid. So x comma t is equal to np dot mesh grid x comma t. So I'm denoting the mesh grid by capital X and capital T. Let me define the implicit function. So it will be np dot exponential of time minus this entire expression. So, or in fact, I can multiply it as well, times 1 upon np dot sine x plus 1 upon np dot tan of x. Essentially what I'm trying to do is to recast this equation as t exponential of t times So I'm trying to cast it in this particular form where x naught is obviously the initial condition for this equation. So now let's see what happens. So I'm defining a function f as this, the left hand side of this, and I want to plot the isoline of f which has this particular value. This is what would be the meaning of creating an implicit plot. Okay, so this is the function, I repeat, this is the function, and I want to plot the isoline which corresponds to this value. If this were to be 0, I would be plotting the 0 isoline of this particular equation. But in this particular case, I would select what x naught would be, and depending on the value of x naught, I would have a different solution. Okay, so let me do this. So I will do plt.contour, and I will say time on the x-axis, x on the y-axis, f, and here I would define the iso value. So iso value is a variable which I will define over here, and this will be equal to this particular thing, but instead of x we will have x naught, so something like this. And I will define what x naught is. So let x naught be equal to pi by 4. Okay, so let me run this and let's see what happens. Great. So when x naught is equal to pi by 4, so disregard this because periodicity would dictate that there is also a solution in this space corresponding to this particular iso value. This is how the evolution would look like. But now whatever this iso value is, so let us print out what the iso value is. It is 2.41. So these three curves, they are the plot, they are like the curves of f in the xt plane which correspond to this particular iso value, and 2 pi and this particular curve. So this particular curve is quite obvious. This particular curve is this particular curve plus 2 pi, because sine and tan, they are periodic in after a period 2 pi. That is, sine of 2 pi plus x naught is the same as tan of 2 pi plus x naught. In fact, if I increase this to 6 pi, we should be able to see more curves. Okay, so it's just an artifact of the fact that everything repeats after 2 pi. So in fact, let me keep it till 3 pi, so that, or in fact, let me keep it till 2 pi itself. So we have just one curve. Okay, don't be confused, it's just a repetition. So now, because of this, we have this particular curve. This is the solution. So essentially this curve is the solution that we're looking for. So let me put some labels. In fact, x-axis is time and this is x. So when we start at a value of pi by 4 over here, in time the value grows and it settles to this value. Now if I change the initial condition, will this evolution in time also appear to be something like this? Obviously not, because when I change the initial condition, it will start from some other point. Let us say that x naught is somewhere over here. It's suppose 4.5. So it starts at 4.5 and in time it decays and it reaches this value. So there has to be something very specific about that value. So let me use the interactivity or in Python and pass x naught as the parameter. So def show solution, and the input will be x naught equal to, let's initialize it at 4.5. Let me put everything inside this function and let me define the interactive widget. So w equal to interactive. Let me pass show sol to this, and x naught will take values from 0.1 all the way to 6.2 in steps of 0.1. So let me run this. Now let me display what W is. Okay, so let us now change the slider. So we see that even though we are changing the initial condition, the curve seems to settle down at this value. Okay, and this value appears to be something like pi. All right, so but there is a change in behavior. So here it is increasing monotonously until this value. It is asymptotically reaching that value. Over here also it is asymptotically reaching that value. But when we are far away from this value, there seems to be a S-like shape. So there's a sigmoid-like shape coming into the picture. Similar over here. So can we geometrically, could we have predicted the presence of that sigmoid kind of function? Let's see. So let us now just plot this. Let me just plot x and sin x. Let us try to understand what actually is going on. So let me define x as np dot linspace. In fact, we have defined it already, but it's wrapped inside a function, so we can define it outside. So 0 to 2 times np dot pi, and dx dt is sine of x. Let me plot it. Okay, so let me plot a vertical, a horizontal line as well. All right. So for what do we have on the x-axis? We have x, and on the y-axis we have dx dt. Okay, so I've kept the plot of sine x over here. So on the y-axis we have dx dt, and on the x-axis we have x. Okay, so what is dx dt? Dx dt is like the velocity of x. Okay, if we consider x to be somewhere on the axis, so dx dt positive would mean, so when dx dt is greater than 0, it would mean the value of x would increase in time. When it is negative, it would mean x would reduce in time. And when dx dt is equal to 0, it means x would not change. Okay, so what this is, so this point where dx dt equal to 0, it is called as a fixed point because the value of x does not change. Okay, so let us analyze whatever is going on over here. So let us consider this as the initial condition. If this is the initial condition, the velocity which corresponds to this initial condition is over here. So if I call this point A, at point A we have dx dt positive. So at the next time instant, it would go, the particle would move to this point. Okay, let me call this point B. So at B, dx dt is again positive, but the magnitude of dx dt is less than the magnitude of the velocity at this point. So the magnitude has reduced. So the velocity has reduced. So in a given time instant, if it traveled this distance, at the next time instant, it will further travel along this, but the distance it would travel would be less. Again, when it would travel the next time instant, the distance it would travel would be less. So if I were to plot x versus time, if it started at this position, x would increase, but at each point, the velocity is dx dt, that is the slope, it would keep on reducing. So you expect this kind of behavior. Okay, and it is sort of reaching the asymptotic point. So when it reaches more and more towards this point where dx dt equal to 0, the velocity is reducing continuously. So that is why that asymptote behavior is there. So if I go over here, that is why this asymptote behavior happens. Okay, it is trying to reach the value of pi, but it will reach it after infinite time. Okay, so that is why that asymptote happens, because velocity over here is large, over here is less. So if you want to interpret the velocity from this curve, it is simply the slope of this curve. It is simply the slope. Okay, so it is taking a curve like this. It is increasing initially fast. Okay, but not increasing initially fast. It is the highest value of the velocity is at the initial point, then the velocity keeps on reducing up until the point it reaches the asymptotic value. Now, what happens when you start off on an initial condition over here? When you start over here the value of the velocity is something like this, but it is positive. So at the next time instant, it will go over here. When it reaches this point, when it reaches a value of higher x, the velocity has increased. So it will move faster towards this region. Okay, because each time you increment x, okay, each time the particle moves towards a higher value of x, the velocity will increase. So there will be a rapid increase in x after this point. So this point corresponds to pi by 2. So after pi by 2, it will increase x, but the velocity will now begin to reduce. So we will have an initial increase. Okay, the value of x will increase and then peak out, and then it will reach the asymptote. Let us see whether that is true. Okay, so initially the slope is increasing as we are moving towards, as we spend more time, as time increases, the slope increases, but after a point the slope then begins to fall. So there is a qualitative change at pi by 2. Similarly, if we look at this point, this point is 3 pi by 2. If we have an initial point over here, okay, over here the velocity is negative, dx dt is negative, so the particle has, the x value will reduce, so it will go towards this. Then the magnitude of velocity has reduced further, so it will very slowly asymptotically reach the value of pi. The value of x will tend towards the value of pi asymptotically. But if you start over here, the magnitude of velocity is small, but and the direction is negative, so x will try to reduce. As it reduces, it will encounter a higher magnitude of velocity, so it will move faster initially. After it crosses 3 pi by 2, the velocity will again start to reduce and it will asymptotically reach the value of pi. So in order to see this in our interactive plot, let us plot pi by 2 and 3 pi by 2 as well. Okay, so let me draw these two contours. So plt dot contour tx x np dot pi upon 2, 3 times np dot pi upon 2. Colors, let us set it to be black. So let me plot this. Okay, so these are the two lines across which we expect a fundamental change in behavior. Okay, so this line is 3 pi by 2, this line is pi, this is pi by 2, this is pi, and this is the time axis. So if we start over here, so if this becomes the initial point, okay, so we are starting between pi by 2 to pi. Okay, let me remove all this. Let me bring this plot over here. Okay, so when we start over here, essentially we are starting at some point over here. So the velocity will continuously decrease up until we reach the equilibrium point. So it will be something like this. Now, if we start at a point somewhere over here that is, the velocity will initially increase, then it will fall. That is, x will rapidly increase in time. X will rapidly increase in time up until it crosses pi by 2, after which it will slowly reach the asymptote. Let us see whether our physical intuition is correct or not. Okay, so it rapidly increases in time. So for a small time duration, we have a rapid increase, so the slope increases, after which it asymptotically tends towards the value of pi. But when we start off with an initial condition over here, it monotonously tries to reach the asymptotic value of pi. Similarly, on the other side, it monotonously decreases to a value of pi, while if we cross this, initially there's a high velocity. The velocity is increasing because you can see the slope is increasing as we go over here up until this point, after which the slope starts to reduce and asymptotically we are tending towards the value of pi. So just like that, without even solving the differential equation, we could have estimated these curves. Okay, as time increases, the value of x is increasing and the slope is increasing because of these reasons that we have discussed. After it crosses pi by 2, that is this point, the velocity begins to reduce despite x increasing, and you will try to asymptotically reach the value of pi. So this is how we could interpret this particular equation, x equal to sine x, or rather x dot is equal to sine x, without actually formally going into the solution. Of course, we could make sense of everything because we had the exact solution with us. Had we not had the exact solution, we could have still predicted these occurrences. We could have said that the slope increases, then slope reduces, and asymptotically we reach pi. Because pi is the fixed point, we must, once it tries to reach pi, the velocity will become 0 and x cannot change anymore. So pi is the fixed point. So just like that, I hope I've shown you a way of interpreting certain equations geometrically. These kind of plots where we are plotting x dot versus x for autonomous systems, they are called as phase plots. And the reason is the nature of the plot. If x dot is positive over here, you know that if this is an initial condition, it will move towards the right, because this point, by virtue of this particular curve, has x dot greater than 0. If you have an initial condition over here, you know that the point will try to move towards the left, because over here x dot is less than 0. So it gives you an idea about how a particle will move on a line. So whatever we are doing is motion on a line. So let us move forward to what is called as the population growth model. Also, it is called as the logistic equation. So in this particular equation, we are trying to model how a population grows. So consider the following equation: dn dt is equal to some rate constant times n. The solution to this is obviously n is equal to n naught exponential of r times t, where at t equal to 0, n is equal to n naught. So it predicts an exponential growth in population. But we all know that such kind of an exponential growth cannot be sustainable because there is a finite amount of resource that you always play with. So in that case, for large values of n, we can say that n dot upon n should then decrease. So n dot upon n is given by minus k So as or rather, what's it? As minus n upon k. So this is kind of a feedback loop that regulates that if n grows quite large, there is a feedback which would try to reduce the population. Okay, so combining these two things, so n dot is obviously the time derivative. We can write down a single equation as n dot is equal to r times n times 1 minus n upon k. So this is the governing equation which, so we sort of estimate that this will be the governing equation, and once we try to look into this equation from a geometrical viewpoint, we will see whether or not this equation can model certain population growth or not. Let us see what the fixed points are. So obviously the fixed point is where n dot is equal to 0. So when n is equal to 0, obviously it's a fixed point. When n is 0, this entire thing becomes 0. And the other condition where n dot becomes 0 is when n is equal to k. So when n equal to k, this becomes 1 and n dot becomes 0. So n equal to 0 and n equal to k are the two fixed points. How does this equation actually look like? So if we draw it like this, n dot on this axis and n on this axis, obviously it will pass through the origin and it will be a parabola which will look something like this. And this is the point n equal to 0 and this is the point n equal to k. Okay, so it is a parabola like this. I mean, what I've drawn is not a parabola, yeah, something like more like this. So let us see what we can infer from this diagram. So obviously there's a maxima over here. Okay, fine. And if we are starting off at 0 population, let's see what happens. I mean, of course, 0 is a fixed point, meaning at n equal to 0, there is no change in n. N dot is identically 0, so nothing. So let us start very close to the origin. At this green point, n dot is positive, meaning the population will grow. So it will move on the line towards this direction. At this particular point, the n dot has increased. So the population will grow quite fast. In the same time, it will grow faster because n dot has increased. Once it reaches this point, then n dot is still positive, so this point will still move to the right. Once it reaches this point, n dot has begun to reduce. So the point will slowly move towards n equal to k. So what we expect the behavior in time is that if you start at low species number, initially there will be a fast rise. Then at certain point there will be a change in the behavior, and there will be a slow, gradual increment of n towards n equal to k, something like this. So this asymptote is n equal to k. Of course, it will take a long time to reach n equal to k. Now, if we have an initial condition over here, somewhere over here, then what happens? We are already at a point where n dot is positive and we are moving towards n equal to k. But now what happens is, as we start moving towards n equal to k, we are in a region where n dot has reduced. So it will slowly move towards n equal to k. So if we start off with a concentration somewhere over here, so this point is k by 2. So suppose this is k by 2. So if we start over here, there will be a monotonous function which will go something like this. We won't have this initial increase and then reduction. Okay, so this sigmoidal kind of behavior will be true when we are starting with low populations. When we already start with population greater than k by 2, we will have a monotonous function like this. So k is called as the carrying capacity, that is the ultimate population. Now what happens when we start at a larger concentration? Somewhere over here. If we start somewhere over here, n dot is negative, so the point will move towards this direction. When we move toward this direction, we have an n dot which is still negative, but it's reduced in magnitude. So it will slowly start moving towards n equal to k. So if we have a population larger than k, then we expect a monotonous reduction in the population until it reaches the carrying capacity. Okay, so this is what we can infer directly from the geometry of the problem without even solving the problem. Okay, so now let us see whether whatever we are predicting is true or not. So let us go to the computer and so let us first, yeah, so in order to do this, we must integrate, we must sort of find a solution to this initial value problem. So this kind of a problem is called as an initial value problem, where you must also specify some initial condition at t equal to 0. Suppose the population is n equal to n naught, and then we can vary n naught and see what happens. Okay, so let us first import the relevant function from scipy. So from scipy dot integrate import solve IVP. So IVP, so solve IVP is the name of the function which resides inside the submodule integrate inside scipy. Okay, so we'll need this, and that's pretty much it. I mean, now we can go ahead and use the function to solve. So I'll talk slightly more about the function once we're done with this. Okay, so let me do this. So let us define what k and r are. So let k be equal to 3, let r be equal to 0.3, let n naught be equal to k by 3. Okay, we can define it in terms of k, fine. And let me define the function handle. So define n dot, and it will take as an input t, it will take, it will output, or rather it will take as an input n also, and the two parameters k and r. So these will be the inputs. So based on this, it should return us the right hand side. So it should return us r times n times 1 minus n upon k. Alright, so now that we have this, let us check whether n dot returns us something. So nd equal to n dot, so 2 n naught kr, and let us print nd. So nd, it returns something, so we're in the green. And in fact, we can easily check this by plotting the whole thing. We can define n equal to np dot linspace minus 1 to 1.5k. Let's take 100 points, and nd will be n dot. So in order, yeah, so it will be n dot t comma, so we have to define what t is. Although the function is autonomous, we still can pass some time, so 2. And actually this plot is independent of time. We are not plotting the time dynamics on this plot, we are just plotting the phase portrait. That's a very important thing to appreciate, and this is simply a face portrait. Alright, so we'll pass time, we'll pass n, we'll pass k and r, and let us then plot. Okay, so we do have that curve that we're looking for, and of course this is the x-axis. Okay, so once we are convinced, we can move ahead and solve this. So let me write the solution as sol is equal to solve underscore ivp. We have to pass the function handle n dot. We have to pass the time span. So let us say we want the time dynamics. So we are looking at the time dynamics over here. So let me plot it till t equal to 20, for example. So time span is the initial time 0 and the final time 20. We'll pass the initial condition n naught, and we'll pass the additional arguments to the function handle. So here's the thing, if you have additional arguments, so ideally a function handle could simply have t and n, and you're actually solving the initial value problem where the independent variable is t, dependent variable is n. Okay, so essentially you will have n versus t, but here our function handle has two additional arguments, k and r. So solve IVP ideally would accept a function which will give output as this, but since we have additional arguments k and r, we need to do the following. We need to pass args equal to, and then we need to pass k comma r in the same sequence as the function, and we will pass the relative tolerance. So r tol equal to 1e minus 6 or 1e minus 6, no problem. So far we have not specified what solver it should use, and we'll discuss initial value problems later on in the course, but for now I just want to show you that this tool exists and you can make use of it to understand things quickly. Just for those of you who are interested, the solve IVP uses the Runge-Kutta 4-5, so 4th, 5th order accuracy, and let us in fact have a look at the contextual help. Okay, so solve IVP, it accepts the function. We have to give the time span, the initial condition. We can additionally specify the method. We can additionally specify at what times you want the output to be. Dense output, these things we'll discuss later on in the course. Events also, perhaps if we have time, we can discuss it. And args. So these are the arguments to the functions. Additionally, there are options which we can pass to the solver. So over here, we can look at all this as well. So method consists of RK45, explicit Runge-Kutta, RK23, explicit Runge-Kutta of reduced order, the dormant prince algorithm, the Radau integration, BDF solver, LSODS solver. So these are various solvers that have been written by very proficient people who spend their lives making things more not only accurate but very efficient to solve on a computer. Okay, and I mean you can spend some time to have a look at it. So we are more interested in the relative tolerance, so we need accurate solutions. Okay, so let's get back to our file. This is how we would call the function. Let us run this. Okay, there's an error. Let's see what has happened. Why not must be one dimensional. Okay, ah, so we must pass it inside as an array. We cannot pass it as a scalar. We must pass it as an array. Okay, so now that we have the solution, let us see what the solution structure actually contains. So solution structure contains solver reached the end of integral, so which is fine. The number of evaluations is 92. T array is this. The y array is this. So we are more interested in the structure sol.t and sol.y. So let us do that. Let us plot sol.t and sol.y. So we will do plt.plot sol.t and sol.y. So the structure sol contains the points the solver has chosen on the x-axis. So we have not specified what times do I want the solution. Given this relative tolerance, the solver will automatically choose the time steps on which it will perform the integration steps. Okay. So the simplest way of doing it, I mean, if you're interested, so dn by dt is some function of n. You would discretize this as some kind of uh, as a forward step. So n at time k minus n at time k minus 1 upon delta t would be function of n at time k minus 1. Okay, this is what you would do. But there are more sophisticated algorithms of doing this, because this method, which is the Euler's method, it suffers from a variety of truncation issues. Okay, it's not very accurate. It's only order delta t accurate. So we use the default solver, which is RK45, and let us plot this. Let us see how it looks. Okay, there's okay. So we have to take a transpose of this. Okay. So here's the plot. So let me put some labels on the plot. So this is going to be time. This is going to be n as a function of time. And you might be wondering why I took a transpose of this object, because when you solve this, it gives, so these are small idiosyncrasies of the output. So t is a single array like this, but y, uh, so by default it assigns the solution to y. So y is something like this. So if you have one variable, y0 is something like this. So you must take a transpose of this so that you can plot these two. Once you take a transpose of this, it will give you something like this, and then you can plot these two. But you cannot plot a row vector with a column vector. That's not possible. That's why this transpose is necessary. So in case you have a system of equations, which we will encounter later in the course, you will have y0 all the values over here, uh, y1 all the values over here. So you have to plot t as a function of this, t as a function of this, and so on. So that's why you need to take a transpose. So this has nothing to do with the techniques and all. It's just something which is inbuilt into the function. Okay, so this is how the plot looks like. Let me enlarge this. Yeah. So we do see that there is a growth and then saturation towards k equal to 3. So in order to see the carrying population, let us plot k equal to 3 line as well. So let us do plt.plot sol.t comma once, rather np.once shape of sol.t and k times this. So it will initiate an array which is all ones multiplied by k. Okay, so it should be np.shape. Okay, and let me make it as a dotted black line. So this is the carrying capacity. All right, this is how it varies. So let us now exploit the interactivity in Python to vary this initial condition and see how the plots look like. So for doing that, we need to wrap everything inside a function. We have already done this. So let me copy this bit. Let me keep this cell as it is. Let me delete this particular cell, or let me use this cell in. So we need to wrap everything in another function. So let us say def plot logistic, and let us pass k and r as the two variables, okay, or the inputs to the function. Let us indent everything inside the function because we want everything inside the plot logistic function. Let me comment out k and r. In fact, let us take as an input n0 as well. So let me comment out this particular thing as well. t, it makes no sense, so let us in fact remove this line. So we have this. This is going to be t end. Let us not hard code this. So t end, and why not? Let us pass t end as an input to the function as well. Let us put default values of 30 and not as 0.2, r as 0.3, and k as 4. So these are the default values. So once we're done with this, let us call w equal to interactive. Then we will pass the function handle which will call the interactive thing. So plot logistic, we will say k goes from 1 to 10 in steps of 0.5, r goes from 0.1 to 0.95 in steps of 0.1, and not should go from 0.1 to 20 in steps of 0.5, and t end should go from 10 to 50 in steps of 10. That's fair enough. Let us display the widget. We have to display the widget as well. So let's have a look. Let's run this and see what happens. Good. So we do have the plot. So right now k is 4 and n naught is smaller than k by 2. So let us in fact plot k by 2 as well. That is a good indicator of the midpoint of the parabola. So let us plot k by 2, and let me make this a red line. Alright, so when n naught is smaller than k by 2, we do have that sigmoidal kind of curve. When we increase this, so you start getting that monotonous increase which we had predicted over here. And once we exceed, we do have a monotonous decrease as we had predicted as well. Alright, so let us change r and c. So if the rate increases, it falls quickly or slowly. So r is like the time constant of this particular plot. Alright, let me reduce this. Okay, so if I reduce this, we get a flatter curve because it would take more time for the population to grow. If I do this, it would take less time for the population to grow. So r is like the rate constant, k is like the carrying population, t end is how long you want the simulation to be. Okay, so this is how we can model the population growth using a very simple model. Obviously this model has various limitations. We're not going to discuss the limitations over here, but it provides a nice way. So if you think about the problem geometrically, it provides you a very convenient means of getting a lot of information without actually solving the problem. Okay, without actually arriving at how n actually varies in time, we could make a fair estimate of how it would actually tend towards the carrying population, or we could see that the population would tend towards the carrying population in the first place. Okay, because it's a fixed point, so we could not only predict the fixed point, but also we could predict how the slope would change as we move towards the fixed point. So with this particular example, I'll end this particular lecture, and I hope you enjoy doing the homework problems. I'll see you again next time with a new lecture. Until then, it's goodbye from me. Bye.